learning objectives. In this chapter, the user would learn the following aspects of combinatorics and recurrence relations: basic theorems on permutation and combination, pigeonhole principle, principle of inclusion and exclusion, ordinary and exponential generating function, recurrence relation, solving recurrence relation by substitution, solving recurrence relation by conversion to linear recurrence relation. History of combinations. Combinatorics. The study of arrangements of objects is an important part of discrete mathematics. The subject was studied as long ago as the 17th century when the combinatorial questions arose in the study of gambling games. Combinations have been applied in all facets of computing, from web technology to mathematical biology. Suppose that a password on a computer system consists of 6, 7 or 8 characters. Each of these characters must be a digit or a letter of the alphabet. Each password must contain at least one digit. How many such passwords are there? Combination is the number of ways of picking k unordered outcomes from n possibilities. There are two techniques used in counting: sum rule, product rule. The product rule applies when a procedure is made up of separate tasks. The product rule. Suppose that a procedure can be broken down into a sequence of two tasks if there are n1 ways to do the first task, and for each of these ways of doing the first task there are n2 ways to do the second task, then there are n1 n2 ways to do the procedure. Another definition: let m be the number of ways to do task 1 and n be the number of ways to do task 2, with each number independent of how the other task is done, and assume that no way to do task 1 simultaneously also accomplishes task 2. The product rule. The task do both task 1 and task 2 can be done in mn ways. A new company with just 2 employees, Sanchez and Patel, rents a floor of a building with 12 offices. How many ways there are to assign different offices to these 2 employees? Solution. The procedure of assigning offices to these 2 employees consists of assigning an office to Sanchez, which can be done in 12 ways. Then assigning an office to Patel, different from the office assigned to Sanchez, which can be done in 11 ways. By the product rule, there are 12 into 11 equal to 132 ways to assign officers to these 2 employees. The chairs of an auditorium are to be labeled with an uppercase English letter followed by a positive integer, not exceeding 100. What is the largest number of chairs that can be labeled differently? Solution. The procedure of labeling a chair consists of 2 tasks, namely assigning to the seat one of the 26 uppercase English letters and then assigning to it one of the 100 possible integers. The product rule shows that there are 26 into 100 equal to 2600 different ways that a chair can be labeled. Therefore, the largest number of chairs that can be labeled differently in 2600. There are 32 microcomputers in a computer center. Each microcomputer has 24 ports. How many different ports to a microcomputer in the center are there? Solution. The procedure of choosing a port consists of 2 tasks. First, picking a microcomputer and then picking a port on this microcomputer, because there are 32 ways to choose microcomputer and 24 ways to choose the port, no matter which microcomputer has been selected. The product rule shows that there are 32 into 24 equal to 768 ports. How many different bit strings of length 7 are there? Solution. Each of the 7 bits can be chosen in 2 ways because each bit is either 0 or 1. Therefore, the product rule shows there are a total of 27 equal to 120 different bit strings of length 7. How many different license plates can be made if each plate contains a sequence of 3 uppercase English letters followed by 3 digits, and no sequences of letters are prohibited even if they are obscene? Solution. There are 26 choices for each of 3 uppercase English letters and 10 choices for each of the 3 digits. Hence, by the product rule, there are a total of 26 into 26 into 26 into 10 into 10 into 10 equal to 17,576,000 possible license plates. What is the value of k after the following code where n1, n2, etc. nm or positive integers has been executed? K equal to 0 for I1 equal to 1 to n1, for I2 equal to 1 to n2, etc. for Im equal to 1 to nm, k equal to k plus 1. Solution. The initial value of k is 0. Each time the nested loop is traversed, 1 is added to k. Let Ti be the task of traversing the ith loop. The number of times the loop is traversed is the number of ways to do the task, T1, T2, etc. Tm. The number of ways to carry out the task Tj, j equal to 1 to etc. m, is the nj because the jth loop is traversed once for the each integer ij, with 1 less than or equal to ij less than or equal to nj. By the product rule, it follows that the nested loop is traversed n1, n2, etc. nm times. Hence, the final value of k is n1, n2, etc. nm. The sum rule. If a task can be done either in one of n1 ways or in one of n2 ways, where none of the set of n1 ways is the same as any of the set of n2 ways, then there are n1 plus n2 ways to do the task. Suppose that either a member of the mathematics faculty or a student who is mathematics major is chosen as a representative to a university committee. How many different choices are there for this representative if there are 37 members of the mathematics faculty and 83 mathematics major and no one is both a faculty member and a student? Solution. There are 37 ways to choose a member of the mathematics faculty and there are 83 ways to choose a student who is mathematics major. Choosing a member of the mathematics faculty is never the same as choosing a student who is mathematics major because no one is both a faculty member and a student. By the sum rule, it follows that there are 37 plus 83 equal to 120 possible ways to pick this representative. A student can choose a computer project from one of the three lists. The three lists contain 23, 15 and 19 possible projects respectively. No project is on more than one list. How many possible projects are there to choose from? Solution. The student can choose a project by selecting a project from the first list, the second list or the third list because no project is on more than one list. By the sum rule, there are 23 plus 15 plus 19 equal to 57 ways to choose a project. Hypothetical rules for passwords. Passwords must contain 2 characters long. Each password must be a letter A to Z, a digit 0 to 9, or one of the 10 punctuation characters. Factorial at, hash, dollar, percentage, hat, ampersand, underscore, brackets. Each password must contain at least one digit or punctuation character. Solution. A legal password has a digit or punctuation character in position 1 or position 2. These cases overlap, so the principle applies. Hash of passwords W, OK symbol in position 1 equal to 10 plus 10 into 10 plus 10 plus 26. Hash of passwords W, OK symbol in position 2 equal to 20 into 46. Hash of passwords W, OK symbol in both places equal to 20 into 20. Answer: 920 plus 920 minus 400 equal to 1440. A computer company receives 350 applications from computer, graduates for a job, planning a line of new web servers. Suppose that 220 of these applicants majored in computer science, 147 majored in business, and 51 majored both in computer science and in business. How many of these applicants majored neither in computer science nor in business? Solution. To find the number of these applicants who majored neither in computer science nor in business, we can subtract the number of students who majored either in computer science or in business or both. From the total number of applicants, let A1 be the set of students who majored in computer science and A2 the set of students who majored in business. Then A1 union A2 is a set of students who majored in computer science or business or both, and A1 intersection A2 is the set of students who majored both in computer science and in business. By the subtraction rule, the number of students who majored either in computer science or in business or both equals A1 union A2 equal to A1 plus A2 minus A1 intersection A2 equal to 220 plus 147 minus 51 equal to 316. We conclude that 350 minus 316 equal to 34 of the applicants majored neither in computer science nor in business. The division rule. We have introduced the product, sum and subtraction rules for counting. You may wonder whether there is also a division rule for counting. In fact, there is such a rule which can be useful when solving certain types of enumeration problems. The division rule, there are n by d ways to do a task if it can be done using a procedure that can be carried out in n ways, and for every day w, exactly d of n ways correspond to way w. Division rule. In terms of sets and functions, if the finite set A is the union of n pairwise disjoint subsets, each with d elements, then n equal to modulus of A by d. If f is a function from A to B, where A and B are finite sets, and that for every value y belongs to B, there are exactly d values x belongs to A, such that f of x equal to y, and in which case we say that f is d to 1, then modulus of B equal to modulus of A by d. How many different ways are there to seat 4 people around a circular table, where 2 seatings are considered the same when each person has the same left neighbor and the same right neighbor? Solution. When arbitrarily select a seat at the table and label it seat 1. B. Number the rest of the seats in numerical order proceeding clockwise around the table. Note that are 4 ways to select the person for seat 1, 3 ways to select the person for seat 2, 2 ways to select the person for seat 3, and 1 way to select the person for seat 4. Thus, there are 4 factorial equal to 24 ways to order the given 4 people for these seats. However, each of the 4 choices for seat 1 leads to the same arrangement, as we distinguish 2 arrangements only when one of the people has a different immediate left or immediate right neighbor, because there are 4 ways to choose the person for seat 1. By the division rule, there are 24 by 4 equal to 6 different seating arrangements of 4 people around the circular table. Pigeonhole principle. Suppose that a flock of 20 pigeons flies into a set of 19 pigeon holes to roost. Because there are 20 pigeons but only 19 pigeon holes, at least one of these 19 pigeon holes must have at least 2 pigeons in it. To see why this is true, note that if each pigeon hole had at most 1 pigeon in it, at most 19 pigeons, 1 per hole could be accommodated, to illustrate a general principle called the pigeonhole principle, which states that if there are more pigeons than pigeon holes, then there must be at least 1 pigeonhole with at least 2 pigeons in it. Of course, this principle applies to other objects besides pigeons and pigeonholes. The pigeonhole principle. If k is a positive integer and k plus 1 or more objects are placed into k boxes, then there is at least 1 box containing 2 or more of the objects. Proof. We prove the pigeonhole principle using a proof by contraposition. Suppose that none of the k boxes contains more than 1 object, then the total number of objects would be at most k. This is a contradiction because there are at least k plus 1 objects. The relation between pigeonhole principle and functions can be shown below. Theorem. A function f from a set with k plus 1 or more elements to a set with k elements is not 1 to 1. Proof. Suppose that for each element y in the codomain of f, we have a box that contains all elements x of the domain of f such that f of x equal to y. Because the domain contains k plus 1 or more elements and the codomain contains only k elements. The pigeonhole principle tells us that one of these boxes contains 2 or more elements x of the domain. This means that f cannot be 1 to 1. There are 280 students in the class. Without knowing anybody's birthday, what is the largest value of n for which we can prove that at least n students must have born in the same month? Answer: modulus of 28 by 12 equal to modulus of 23.3 equal to 24. Show that for every integer n, there is a multiple of n that has zeros and ones in its decimal expansion. Solution: let n be a positive integer. Consider the n plus 1 integers 1, 1, 1, 1, 1, 1, etc. 1, 1, etc. 1. But the last integer in this list is the integer with n plus 1 ones in its decimal expansion. Note that there are n possible remainders where an integer is divided by n. Because there are n plus 1 integers in this list, by the pigeonhole principle, there must be 2 with the same remainder. When divided by n, the larger of these integers less the smaller one is a multiple of n, which has a decimal expansion consisting entirely of zeros and ones. The generalized pigeonhole principle. If n objects are placed into k boxes, then there is at least one box containing at least n by k objects. Proof. We will use a proof by contraposition. Suppose that none of the boxes contains more than n by k minus 1 objects, then the total number of objects is at most k into n by k minus 1 less than k into n by k plus 1 minus 1 equal to n, where the inequality n by k less than n by k plus 1 has been used. This is a contradiction because there are a total of n objects. What is the minimum number of students required in a discrete mathematics class to be sure that at least 6 will receive the same grade if there are 5 possible grades A, B, C, D and F? Solution. The minimum number of students needed to ensure that at least 6 students receive the same grade is the smallest integer n, such that n by 5 equal to 6. The smallest such integer is n equal to 5 into 5 plus 1 equal to 26. If you have only 25 students, it is possible for there to be 5 who have received each grade so that no 6 students have received the same grade. Thus, 26 is the minimum number of students needed to ensure that at least 6 students will receive the same grade. What is the least number of area codes needed to guarantee that the 25 million phones in a state can be assigned distinct 10-digit telephone numbers? Assume that telephone numbers are of the form NXX-NXX-XXXX, where the first 3 digits form the area code, n represents a digit from 2 to 9 inclusive, and x represents any digit. Solution. There are 8 million different phone numbers of the form NXX-XXXX as shown in example 8 of section 6.1. Hence, by the generalized pigeonhole principle, among 25 million telephones, at least 25 lakhs by 8 lakhs equal to 4 of them must have identical phone numbers. Hence, at least 4 area codes are required to ensure that all 10-digit numbers are different. During a month with 30 days, a baseball team plays at least one game a day but no more than 45 games. Show that there must be a period of some number of consecutive days during which the team must play exactly 14 games. Solution. Let AJ be the number of games played on or before the jth day of the month. Then A1, A2, etc. A30 is an increasing sequence of distinct positive integers with 1 less than or equal to AJ less than or equal to 45. Moreover, A1 plus 14, A2 plus 14, etc. A30 plus 14 is also an increasing sequence of distinct positive integers with 15 less than or equal to AJ plus 14 less than or equal to 59. The 60 positive integers A1, A2, etc. A30, A1 plus 14, A2 plus 14, etc. A30 plus 14 are all less than or equal to 59. Hence, by the pigeonhole principle, 2 of these integers are equal because the integers AJ, J equal to 1, 2, 3, etc. 30 are all distinct, and the integers AJ plus 14, J equal to 1, 2, 3, etc. 30 are all distinct. There must be indices I and J with AI equal to AJ plus 14. This means that exactly 14 games were played from day J plus 1 to day I. Assume that in a group of 6 people, each pair of individuals consists of 2 friends or 2 enemies. Show that there are either 3 mutual friends or 3 mutual enemies in the group. Solution. Let A be one of the 6 people, one of the 5 other people in the group. There are either 3 or more who are friends of A or 3 or more who are enemies of A. This follows from the generalized pigeonhole principle, because when 5 objects are divided into 2 sets, one of the sets has at least 5 by 2 equal to 3 elements. In the former case, suppose that B, C and D are friends of A. If any two of these 3 individuals are friends, then these 2 and A form a group of 3 mutual friends. Otherwise, B, C and D form a set of 3 mutual enemies. The proof in the later case, when there are 3 or more enemies of A, proceeds in a similar manner. The Ramsey number or of m, n, where m and n are positive integers greater than or equal to 2, denotes the minimum number of people at a party such that there are either mutual friends or n mutual enemies, assuming that every pair of people at the party are friends or enemies. The example shows that r of 3, 3 less than or equal to 6. We conclude that r of 3, 3 equal to 6 because in a group of 5. Many counting problems can be solved by finding the number of ways to arrange a specified number of distinct elements of a set of particular size when the order of these elements matters. Many other counting problems can be solved by finding the number of ways to select a particular number of elements from a set of particular size where the order of the elements selected does not matter. For example, in how many ways can we select 3 students from a group of 5 students to stand in line for a picture? How many different committees of 3 students can be formed from a group of 4 students? Permutations and combinations offer methods to answer questions such as these. A permutation of a set S of objects is a sequence containing each object once. An ordered arrangement of or distinct elements of S is called an OR permutation. For example, in how many ways can we select 3 students from a group of 5 students to stand in line for a picture? In how many ways can we arrange all 5 of these students in a line for a picture? Solution. First, note that the order in which we select the students matters. There are 5 ways to select the first student to stand at the first of the line. Once the student has been selected, there are 4 ways to select the second student in the line. After the first and second students have been selected, there are 3 ways to select the third student in the line by the product rule. There are 5 into 4 into 3 equal to 60 ways to select 3 students from a group of 5 students to stand in line for a picture. To arrange all 5 students in a line for a picture, we select the first student in 5 ways, the second in 4 ways, the third in 3 ways, the fourth in 2 ways and the fifth in 1 way. Consequently, there are 5 into 4 into 3 into 2 into 1 equal to 120 ways to arrange all 5 students in a line for a picture. The number of OR permutations of a set with n elements is denoted by P of n, r. If n is a positive integer and r is an integer with 1 less than or equal to or less than or equal to n, then there are P of n, r equal to n into n minus 1, n minus 2, etc., n minus r plus 1. Or permutations of a set with n distinct elements. Proof. We will use the product rule to prove that this formula is correct. The first element of the permutation can be chosen in n ways because there are n elements in the set. There are n minus 1 ways to choose the second element of the permutation because there are n minus 1 elements left in the set after using the element picked for the first position. Similarly, there are n minus 2 ways to choose the third element and so on until there are exactly n minus r minus 1 equal to n minus r plus 1 ways to choose the rth element. Consequently, by the product rule, there are n into n minus 1, n minus 2, etc., n minus r plus 1 or permutations of the set. Note that P of n, 0 equal to 1 whenever n is a non-negative integer because there is exactly one way to order 0 elements. That is, there is exactly one list with no elements in it, namely the empty list. How many ways are there to select a first prize winner, a second prize winner and a third prize winner from 100 different people who have entered a contest? Solution. Because it matters which person wins which prize. The number of ways to pick the 3 prize winners is the number of ordered selections of 3 elements from a set of 100 elements. That is, the number of 3 permutations of a set of 100 elements. Consequently, the answer is P of 100, 3 equal to 100 into 99 into 98 equal to 970,200. Suppose that there are 8 runners in a race. The winner receives a gold medal, the second place winner receives a silver medal and the third place finisher receives a bronze medal. How many different ways there are to award these medals? If all possible outcomes of the race can occur and there are no ties. Solution. The number of different ways to award the medals is the number of 3 permutations of a set with 8 elements. Hence, there are P of 8, 3 equal to 8 into 7 into 6 equal to 336 possible ways to award the medals. Suppose that a saleswoman has to visit 8 different cities. She must begin a trip in a specified city, but she can visit the other 7 cities in any order she wishes. How many possible orders can the saleswoman use when visiting these cities? Solution. The number of possible paths between cities is the number of permutations of 7 elements because the first city is determined, but the remaining 7 cities can be ordered arbitrarily. Consequently, there are 7 factorial equal to 7 into 6 into 5 into 4 into 3 into 1 equal to 5040 ways for the saleswoman to choose a tour. If, for instance, the saleswoman wishes to find the path between the cities with minimum distance and she computes the total distance for each possible path, she must consider a total of 5040 paths factorial. How many permutations of the letters A, B, C, D, E, F, G, H contain the string ABC? Solution. Because the letters ABC must occur as a block, we can find the answer by finding the number of permutations of 6 objects, namely the block ABC and the individual letters D, E, F, G and H. Because these 6 objects can occur in any order, there are 6 factorial equal to 720 permutations of the letters A, B, C, D, E, F, G, H, in which ABC occurs as a block. An OR combination of elements of a set is an unordered selection of OR elements from the set. Thus, an OR combination is simply a subset of the set with OR elements. How many different committees of 3 students can be formed from a group of 4 students? Solution. To answer this question, we need only find the number of subsets with 3 elements. From the set containing the 4 students, we see that there are 4 such subsets, one for each of the 4 students. Because choosing 3 students is the same as choosing one of the 4 students to leave out of the group. This means that there are 4 ways to choose the 3 students for the committee, where the order in which these students are chosen does not matter. The number of OR combinations of a set with n distinct elements is denoted by C of n, R. C of n, R is called a binomial coefficient. The number of OR combinations of a set with n distinct elements is denoted by C of n, R. The number of OR combinations of a set with n elements where n is a non-negative integer and R is an integer with 0 less than or equal to or less than or equal to n equals C of n, R equal to n factorial divided by R factorial into n minus R factorial. The P of n, R are permutations of the set can be obtained by forming the C of n, R or combinations of the set and then ordering the. How many poker hands of 5 cards can be dealt from a standard deck of 52 cards? Also, how many ways are there to select 47 cards from a standard deck of 52 cards? Solution. Because the order in which the 5 cards are dealt from a deck of 52 cards does not matter. There are C of 52, 5 equal to 52 factorial by 5 factorial into 47 factorial. Different hands of 5 cards that can be dealt to compute the value of C of 52, 5. First divide the numerator and denominator by 47 factorial to obtain C of 52, 5 equal to 52 into 51 into 50 into 49 into 48 by 5 into 4 into 3 into 2 into 1. Let n and r be non-negative integers with r less than or equal to n. Then C of n, r equal to C of n, n minus r. How many ways are there to select 5 players from a 10-member tennis team to make a trip to a match at another school? Solution. The answer is given by the answer of 5 combinations of a set with 10 elements by theorem 2. The number of such combinations is C of 10, 5 equal to 10 factorial by 5 factorial into 5 factorial equal to 252. A group of 30 people have been trained as astronauts to go on the first mission to Mars. How many ways are there to select a crew of 6 people to go on this mission, assuming that all crew members have the same job? Solution. The number of ways to select a crew of 6 from the pool of 30 people is the number of 6 combinations of a set with 30 elements, because the order in which these people are chosen does not matter. By theorem 2, the number of such combinations is C of 30, 6 equal to 30 factorial by 6 factorial into 24 factorial equal to 30 into 29 into 28 into 27 into 26 into 25 by 6 into 5 into 4 into 3 into 2 into 1 equal to 593,775. The number of OR permutations of a set of n objects with repetition allowed is n power r. Proof. There are n ways to select an element. The set for each of the OR positions in the OR permutation when repetition is allowed, because for each choice all n objects are available. Hence, by the product rule, there are n power r OR permutations when repetition is allowed. How many strings of length r can be formed from the uppercase letters of English alphabet? Solution. By the product rule, because there are 26 uppercase English letters and because each letter can be used repeatedly, we see that there are 26 power r strings of uppercase English letters of length r. There are C of n plus r minus 1, r or combinations from a set with n elements when repetition of elements is allowed. Proof. Each OR combination of a set with n elements when repetition is allowed can be represented by a list of the n-1 bars and r stars. The n-1 bars are used to do mark of n different cells with the ith cell containing a star for each time the ith element of the set occurs in the combination. For instance, a 6 combination of a set with 4 elements is represented with 3 bars and 6 stars. Here, star, 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 star represents the combination containing exactly 2 of the first element, 1 of the second element, none of the third element, and 3 of the fourth element of the set. As we have seen, each different list containing n-1 bars and r stars corresponds to an OR combination of the set with n elements. When repetition is allowed, the number of such lists is C of n-1 plus r, r, because each list corresponds to a choice of the OR positions to place the r stars from the n-1 plus r positions that contain r stars and n-1 bars. The number of such lists is also equal to C of n-1 plus r, n-1, because each list corresponds to a choice of the n-1 positions to place the n-1 bars. Suppose that a cookie shop has 4 different kinds of cookies. How many different ways can 6 cookies be chosen? Assume that only the type of cookie and not the individual cookies or the order in which they are chosen matters. Solution. The number of ways to cookies, number of 6 combinations of a set with 4 elements. From theorem 2, this equals C of 4 plus 6 minus 1, 6 equal to C of 9, 6, because C of 9, 6 equal to C of 9, 3 equal to 9 into 8 into 7, 1 into 2 into 3 equal to 84. There are 84 different ways to choose the 6 cookies. Permutations with indistinguishable objects. Some elements may be indistinguishable in counting problems. When this is the case, care must be taken to avoid counting things more than once. How many different strings can be made by recording the letters of the word success? Solution. Because some of the letters of success are the same, the answer is not given by the number of permutations of 7 letters. This word contains 3 S's, 2 C's, 1 U and 1 E. To determine the number of different strings that can be made by reordering the letters, first note that the 3 S's can be placed among the 7 positions in C of 7, 3 different ways, leaving 4 positions free. Then the 2 C's can be placed in C of 4, 2 ways, leaving 2 free positions. The U can be placed in C of 2, 1 ways, leaving just 1 position free. Hence, E can be placed in C of 1, 1 ways. Consequently, from the product rule, the number of different strings that can be made is C of 7, 3, C of 4, 2, C of 2, 1, C of 1, 1 equal to 7 factorial by 3 factorial into 4 factorial into 4 factorial by 2 factorial into 2 factorial into 2 factorial by 1 factorial into 1 factorial into 1 factorial by 1 factorial into 0 factorial equal to 7 factorial by 3 factorial into 2 factorial into 1 factorial into 1 factorial equal to 420. The number of different permutations of n objects where there are n1 indistinguishable objects of type 1, n2 indistinguishable objects of type 2, etc. and nk indistinguishable objects of type k is n factorial by n1 factorial, n2 factorial, etc. nk factorial. Proof. To determine the number of permutations, first note that the n1 objects of type 1 can be placed among the n positions in C of n, n1 ways, leaving n minus n1 positions free. Then the objects of type 2 can be placed in C of n minus n1, n2 ways, leaving n minus n1 minus n2 positions free. Continue placing the objects of type 3, etc., type k minus 1 until at the last stage nk objects of type k can be placed in C of n minus n1 minus n2 minus etc. minus nk minus 1, nk ways. Hence, by the product rule, the total number of different permutations is C of n, n1, C of n minus n1, n2, etc., C of n minus n1 minus etc. minus nk minus 1, nk equal to n factorial by n1 factorial into n minus n1 factorial into n minus n1 factorial by n2 factorial into n minus n1 minus n2 factorial, etc. n minus n1 minus etc. minus nk minus 1 factorial by nk factorial into 0 factorial equal to n factorial by n1 factorial, n2 factorial, etc. nk factorial. Combinatorics and probability theory share common origins. The theory of probability was first developed more than 300 years ago when certain gambling games were analyzed. Although probability theory was originally invented to study gambling, it now plays an essential role in a wide variety of disciplines. For example, probability theory is extensively applied in the study of genetics, where it can be used to help understand the inheritance of traits. Of course, probability still remains an extremely popular part of mathematics because of its applicability to gambling, which continues to be an extremely popular human endeavor. An experiment is a procedure that yields one of a given set of possible outcomes. The sample space of the experiment is the set of possible outcomes. An event is a subset of the sample space. Laplace definition of the probability of an event with finitely many possible outcomes will now be stated. Definition 1. If S is a finite non-empty sample space of equally likely outcomes and E is an event that is a subset of S, then the probability of E is P of E equal to modulus of E by modulus of S. The probability of an event can never be negative or more than 1 factorial. According to Laplace definition, the probability of an event is between 0 and 1. To see this, note that if E is an event from a finite sample space S, then 0 less than or equal to modulus of E less than or equal to modulus of S, because where E is a subset of S. Thus, 0 less than or equal to P of E equal to modulus of E by modulus of S less than or equal to 1. An urn contains 4 blue balls and 5 red balls. What is the probability that a ball chosen at random from the urn is blue? Solution. To calculate the probability, note that there are 9 possible outcomes and 4 of these possible outcomes produce a blue ball. Hence, the probability that a blue ball is chosen is 4 by 9. In a lottery, players win a large prize when they pick 4 digits that match in the correct order. 4 digits selected by random mechanical process. A smaller prize is won if only 3 digits are matched. What is the probability that a player wins the large prize? What is the probability that a player wins a small prize? Solution. There is only one way to choose all 4 digits correctly. By the product rule, there are 104 equal to 10,000 ways to choose 4 digits. Hence, the probability that a player wins a large prize is 1 by 10,000 equal to 0.0001. players win the smaller prize when they correctly choose exactly 3 of the 4 digits. Exactly 1 digit must be wrong to get 3 digits correct, but not all 4 correct. By the sum rule, to find the number of ways to choose exactly 3 digits correctly, we add the number of ways to choose 4 digits matching the digits picked in all but the ith position for I equal to 1, 2, 3, 4. To count the number of successes with the first digit incorrect, note that there are 9 possible choices for the first digit, all but the one correct digit, and one choice for each of the other digits, namely the correct digits for these slots. Hence, there are 9 ways to choose 4 digits where the first digit is incorrect but the last 3 are correct. Similarly, there are 9 ways to choose 4 digits where the second digit is incorrect, 9 with the third digit incorrect, and 9 with the fourth digit incorrect. Hence, there is a total of 36 ways to choose 4 digits with exactly 3 of the 4 digits correct. Thus, the probability that a player wins a smaller prize is 36 by 10,000 equal to 9 by 2,500 equal to 0.0036. There are many lotteries now that award enormous prizes to people who correctly choose a set of 6 numbers out of the first n positive integers, where n is usually between 30 and 60. What is the probability that a person picks the correct 6 numbers out of 40? Solution: there is only one winning combination. The total number of ways to choose 6 numbers out of 40 is C of 40, 6 equal to 40 factorial by 34 factorial into 6 factorial equal to 3,838,380. Consequently, the probability of picking a winning combination is 1 divided by 3,838,380, approximately equal to 0.000000026. What is the probability that the numbers 11, 4, 17, 39 and 23 are drawn in that order from a bin containing 50 balls labeled with the numbers 1, 2, etc. 50? If A, the ball selected is not returned to the bin before the next ball is selected, and B, the ball selected is returned to the bin before the next ball is selected. Solution: by the product rule, there are 50 into 49 into 48 into 47 into 46 equal to 254 lakhs 251,200 ways to select the balls. Because each time a ball is drawn, there is one fewer ball is to choose from. Consequently, the probability that 11, 4, 17, 39 and 23 are drawn in that order is 1 divided by 254 lakhs 251,200. This is an example of sampling without replacement. B. By the product rule, there are 505 equal to 312 lakhs, 500,000 ways to select the balls. Because there are 50 possible balls to choose from each time a ball is drawn. Consequently, the probability that 11, 4, 17, 39 and 23 are drawn in that order is 1 divided by 312 lakhs 500,000. This is an example of sampling with replacement. A sequence of 10 bits is randomly generated. What is the probability that at least one of these bits is 0? Solution: let E be the event that at least one of the 10 bits is 0. Then E is the event that all the bits are 1s. Because the sample space S is the set of all bit strings of length 10, it follows that P of E equal to 1 minus P of E equal to 1 minus 1 by 1024 equal to 1023 by 1024. Hence, the probability that the bit string will contain at least one 0 bit is 1023 divided by 1024. The Monty Hall 3-door puzzle. Suppose you are a game show contestant. You have a chance to win a large prize. You are asked to select one of the 3 doors to open. The large prize is behind one of the 3 doors and the other 2 doors are losses. Once you select a door, the game show host, who knows what is behind each door, does the following. First, whether or not you select the winning door, he opens one of the two doors that he knows is a losing door, selecting at random if both are losing door. Then he asks you whether you would like to switch doors. Which strategy should you use? Should you change doors or keep your original selection, or does it not matter? Solution: the probability you select the correct door before the host opens a door and asks you whether you want to change is 1 by 3, because the 3 doors are equally like to be the correct door. The probability this is the correct door does not change once the game show host opens one of the other doors, because he will always open a door that the price is not behind. The probability that you selected incorrectly is the probability the price is behind one of the two doors you did not select. Consequently, the probability that you selected incorrectly is 2 by 3. If you selected incorrectly when the game show host opens a door to show you that the price is not behind it, the price is behind the other door, you will always win if your initial choice was incorrect and you change doors. So by changing doors, the probability you win is 2 by 3. In other words, you should always change doors when given the chance to do so by the game show host. This doubles the probability that you will win. To understand recurrence relation, let us start from the basics. Sequences. A sequence is a discrete structure used to represent an order list. For example, 1, 2, 3, 5, 8 is a sequence with 5 terms, and 1, 3, 9, 27, 81, etc. 3n, etc. is an infinite sequence. Definition 1. A sequence is a function from a subset of the set of integers, usually either the set 0, 1, 2, etc. or the set 1, 2, 3, etc. To a set S, we use the notation an to denote the image of the integer n. We call an a term of the sequence. A recurrence relation for the sequence an is an equation that expresses an in terms of one or more of the previous terms of the sequence, namely a0, a1, etc. an minus 1 for all integers n with n greater than or equal to n0. Where n0 is a non-negative integer, a sequence is called a solution of recurrence relation if its terms satisfy the recurrence relation B. Let an be a sequence that satisfies a recurrence relation an equal to an minus 1 plus 3 for n equal to 1 to 3, and suppose that a0 equal to 2. What are a1, a2 and a3? Solution. We see from the recurrence relation that a1 equal to a0 plus 3 equal to 2 plus 3 equal to 5. It then follows that a2 equal to 5 plus 3 equal to 8 and a3 equal to 8 plus 3 equal to 11. Initial conditions for a recursively defined sequence specify the terms that precede the first term where the recurrence relation takes effect. For instance, the initial condition in example 5 is a0 equal to 2. The Fibonacci sequence f0, f1, f2, etc. is defined by the initial conditions f0 equal to 0, f1 equal to 1, and the recurrence relation fn equal to fn minus 1 plus fn minus 2 for n equal to 2, 3, 4, etc. Compound interest. Suppose that a person deposits $10,000 in a savings account at a bank, yielding 11% per year with interest compounded annually. How much will be in the account after 30 years? Solution. To solve this problem, let Pn denote the amount in the account after n years, because the amount in the account after n years equals the amount in the account after n minus 1 years plus interest for the nth year. We see that the sequence Pn satisfies the recurrence relation Pn equal to Pn minus 1 plus 0.11 Pn minus 1 equal to 1.11 Pn minus 1. The initial condition is P0 equal to 10,000. We can use an iterative approach to find a formula for Pn. Note that P1 equal to 1.11 into P0, P2 equal to 1.11 into P1 equal to 1.11 into 2 P0, P3 equal to 1.11 into P2 equal to 1.11 into 3 into P0, etc. Pn equal to 1.11 Pn minus 1 equal to 1.11 into n P0. When we insert the initial condition P0 equal to 10,000, the formula Pn equal to 1.11 into n 10,000 is obtained. Inserting n equal to 30 into the formula Pn equal to 1.11 into n 10,000 shows that after 30 years the account contains P30 equal to 1.11, 3,10,000 times equal to $228,922.97. A common problem in discrete mathematics is finding a closed formula, a recurrence relation, or some other type of general rule for constructing the term of a sequence. Sometimes only a few terms of a sequence solving a problem are known. The goal is to identify the sequence. Find formulae for the sequences with the following first 5 terms: A 1, 1 by 2, 1 by 4, 1 by 8, 1 by 16. B 1, 3, 5, 7, 9. C 1, minus 1, 1, minus 1, 1. Solution. A. We recognize that the denominators are powers of 2. The sequence with an equal to 1 by 2n, n equal to 0, 1, 2, etc. is a possible match. This proposed sequence is a geometric progression with a equal to 1 and r equal to 1 by 2. B. We note that each term is obtained by adding 2 to the previous term. The sequence with an equal to 2n plus 1, n equal to 0, 1, 2, etc. is a possible match. This proposed sequence is an arithmetic progression with a equal to 1 and d equal to 2. C. The terms alternate between 1 and minus 1. The sequence with an equal to minus 1 into n equal to 0, 1, 2, etc. is a possible match. This proposed sequence is a geometric progression with a equal to 1 and r equal to minus 1. How can we produce the terms of a sequence if the first 10 terms are 1, 2, 2, 3, 3, 3, 4, 4, 4, 4? Solution. In the sequence, the integer 1 appears once, the integer 2 appears twice, the integer 3 appears 3 times, the integer 4 appears 4 times. A reasonable rule for generating this sequence is that the integer n appears exactly n times. So the next 5 terms of the sequence would all be 5, and the following 6 terms would all be 6, and so on. The sequence generated this way is a possible match. Recursively defined function. We use 2 steps to define a function with a set of non-negative integers as its domain. Basic step. Specify the value of the function at 0. Recursive step. Give a rule for finding its value at an integer from its value at smaller integers. Such definition is called a recursive or inductive definition. Note that the function f of n from the set of non-negative integers to the set of real numbers is the same as the sequence a0, a1, etc., where ai is a real number for every non-negative integer I. So defining a real valued sequence a0, a1, etc. using a recurrence relation, as was done in section 2.4, is the same as defining a function from the set of non-negative integers to the set of real numbers. Suppose that f is defined recursively by f of 0 equal to 3, f of n plus 1 equal to 2 times of f of n plus 3. Find f of 1, f of 2, f of 3 and f of 4. Solution. From the recursive definition, it follows that f of 1 equal to 2 times of f of 0 plus 3 equal to 2 into 3 plus 3 equal to 9. F of 2 equal to 2 times of f of 1 plus 3 equal to 2 into 9 plus 3 equal to 21. F of 3 equal to 2 into f of 2 plus 3 equal to 2 into 21 plus 3 equal to 45. F of 4 equal to 2 into f of 3 plus 3 equal to 2 into 45 plus 3 equal to 93. Recursively defined functions are well defined. That is, for every positive integer, the value of the function at this integer is determined in an unambiguous way. This means that given any positive integer, we can use the 2 parts of the definition, find the value of the function at the integer, and that we obtain the same value no matter how we apply the 2 parts of the definition. This is a consequence of the principle of mathematical induction. Consider this problem, which was originally posed by Fibonacci in the 13th century in this book, Liber Abaci. A young pair of rabbits, one of each sex, is placed on an island. A pair of rabbits does not breed until they are 2 months old. After the 2 months old, each pair of rabbits produce another each month as shown in figure 1. Find a recurrence relation for the number of pairs of rabbits. on the island after n months, assuming that no rabbits ever die. Solution. Denoted by Fn, the number of pairs of rabbits after n months, we will show that Fn, n equal to 1, 2, 3, etc. are the terms of the Fibonacci sequence. The rabbit population can be modeled using a recurrence relation. At the end of the first month, the number of pairs of rabbits on the island is F1 equal to 1. Because this pair does not breed during the second month, F2 equal to 1 also. To find the number of pairs after n months, add the Fibonacci numbers appear in many other places in nature, including the number of petals on flowers and the number of spirals on seed heads. The number on the island the previous month Fn minus 1 and the number of newborn pairs which equals Fn minus 2, because each newborn pair comes from a pair at least 2 months old. Consequently, the sequence Fn satisfies the recurrence relation Fn equal to Fn minus 1 plus Fn minus 2 for n greater than or equal to 3, together with the initial conditions F1 equal to 1 and F2 equal to 1. Because this recurrence relation and the initial conditions uniquely determine the sequence, the number of pairs of rabbits on the island after n months is given by the nth Fibonacci numbers. A popular puzzle of the late 19th century, invented by French mathematician Edouard Lucas, called the Tower of Hanoi, consists of 3 pegs mounted on a board together with the discs of different sizes. Initially, these discs are placed on the first peg in order of size, with the largest on the bottom, as shown in figure. The rule of the puzzle also disc to be moved one at a time from one peg to another as long as the disc is never placed on the top of a smaller disc. The goal of the puzzle is to have all the discs on the second peg in order of size with the largest on the bottom. Solution. Begin with n disc on peg 1. We can transfer the top n minus n disc following the rules of the puzzle to peg 3 using hn minus n moves. See figure for an illustration of the pegs and disc at this point. We keep the largest disc fixed during these moves. Then we use one move to transfer the largest disc to the second peg. We can transfer the n minus 1 disc on peg 3 to peg 2 using hn minus 1 addition moves, placing them on top of the largest disc, which always stays fixed on the bottom of peg 2. Moreover, it is easy to see that the puzzle cannot be solved using fewer schemes for efficiently backing up computer files on multiple tapes or other media, or based on the moves used to solve the Tower of Hanoi puzzle steps. This shows that hn equal to 2hn minus 1 plus 1. The initial condition is h1 equal to 1 because one disc can be transferred from peg 1 to peg 2 according to the rules of the puzzle in one move. Code word enumeration. A computer system considers a string of decimal digits a valid code word if it contains an even number of 0 digits. For instance, 1, 2, 3, 0, 4, 0, 7, 8, 6, 9 is valid, whereas 1, 2, 0, 9, 8, 7, 0, 4, 5, 6, 0, 8 is not valid. Let an be the number of valid n-digit code words. Find a recurrence relation for an. Solution. Note that a1 equal to 9 because there are 10 one-digit strings and only one, namely, the string 0 is not valid. A recurrence relation can be derived for this sequence by considering how a valid n-digit string can be obtained from strings of n-1 digits. There are two ways to form a valid string with n digits from a string with one fewer digit. First, a valid string of n digits can be obtained by appending a valid string of n-1 digits with a digit other than 0. This appending can be done in 9 ways. Hence, a valid string with n digits can be formed in this manner in 9 an-1 ways. Second, a valid string of n digits can be obtained by appending a 0 to a string of length n-1 that is not valid. This produces a string with an even number of 0 digits because the invalid string of length n-1 has an odd number of 0 digits. the number of ways that is can be done equals the number of invalid n-1 digit strings, because there are 10 n-1 strings of length n-1 and an-1 are valid. There are 10 n-1 minus an-1 valid n-digit strings obtained by appending an invalid string of length n-1 with a 0. Because all valid strings of length n are produced in one of these two ways, it follows that there are an equal to 9 an-1 plus 10 n-1 minus an-1 equal to 8 an-1 plus 10 n-1 valid strings of length n. Many recursive algorithms take a problem with a given input and divide it into one or more smaller problems. This reduction is successively applied until the solutions of the smaller problems can be found quickly. These procedures follow an important algorithmic paradigm known divide impera translation, divide and conquer. Julius Caesar as divide and conquer and are called divide and conquer algorithms because they divide a problem into one or more instances of the same problem of smaller size, and they conquer the problem by using the solutions of the smaller problems to find a solution of the original problem, perhaps with some additional work. Divide and conquer examples. For instance, we perform a binary search by reducing the search for an element in a list to the search for this element in a list of as long. We successively apply this reduction until one element is left. When we sort a list of integers using the merge sort, we split the list into two halves of equal size and sort each half separately. We then merge the two sorted halves. Another example of this type of recursive algorithm is a procedure for multiplying integers that reduces the problem of the multiplication of two integers to three multiplications of pairs of integers with half as many bits. This reduction is successively applied until integers with one bit are obtained. Divide and conquer recurrence relations. Suppose that a recursive algorithm divides a problem of size n into a subproblems where each subproblem is of size n by b. For simplicity, assume that n is a multiple of b. In reality, the smaller problems are often of size equal to the nearest integers, either less than or equal to or greater than or equal to n by b. Also, suppose that a total of g of n extra operations are required in the conquer step of the algorithm to combine the solutions of the subproblems into a solution of the original problem. Then, if f of n represents the number of operations required to solve the problem of size n, it follows that f satisfies the recurrence relation f of n equal to a f of n by b plus g of n. This is called a divide and conquer recurrence relation. Finding the maxima and minima of a sequence. Consider the following algorithm for locating the maximum and minimum elements of a sequence a1, a2, etc. an. If n equal to 1, then a1 is the maximum and the minimum. If n greater than 1, the split the sequence into two sequences, either where both have the same number of elements or when one of the sequences has one more element than the other. The problem is reduced to finding the maximum and minimum of each of the two smaller sequences. The solution to the original problem results from the comparison of the separate maxima and minima of the two smaller sequences to obtain the overall maximum and minimum. Let f of n be the total number of comparisons needed to find the maximum and minimum elements of the sequence with n elements. We have shown for that problem of size n can be reduced into two problems of size n by 2. When n is even, using two comparisons, one to compare and the maxima of the two sequences and the other to compare the minima of the two sequences. This gives the recurrence relation f of n equal to 2 times of f of n by 2 plus 2 when n is even. Merge sort. The merge sort algorithm splits a list to be sorted with n items when n is even into two lists with n by 2 elements each, and uses fewer than n comparisons to merge the two sorted list of n by 2 items each into one sorted list. Consequently, the number of comparisons used by the merge sort to sort a list of n elements is less than m of n, where the function m of n satisfies the divide and conquer recurrence relation m of n equal to 2 times of m of n by 2 plus n. Generating functions are used to represent sequences efficiently by coding the term of a sequence as coefficients of powers of a variable x in a formal power series. Generating functions can be used to solve many types of counting problems, such as the number of ways to select or distribute objects of different kinds subject to a variety of constraints, and the number of ways to make change for a dollar using coins of different denominations. Generating functions can be used to solve recurrence relations by translating a recurrence relation for the terms of a sequence into an equation involving a generating function. The generating function for the sequence a0, a1, a2, etc., ak, etc. of real numbers is the infinite series g of x equal to a0 plus a1x plus etc. plus ak into x power k plus etc. equal to summation k equal to 0 to infinity ak into x power k. What is the generating function of the sequence 1, 1, 1, 1, 1, 1? Solution. The generating function is 1, 1, 1, 1, 1, 1 is 1 plus x square plus x cube plus x power 4 plus x power 5. By theorem 1 of section 2.4, we have x power 6 minus 1 by x minus 1 equal to 1 plus x square plus x cube plus x power 4 plus x power 5. When x not equal to 1, consequently g of x equal to x power 6 minus 1 by x minus 1 is the generating function of the sequence 1, 1, 1, 1, 1, 1. Because the powers of x are only placeholders for the terms of the sequence in generating function, we do not need to worry that g of 1 is undefined. Let m be a positive integer. Let ak equal to c of m comma k for k equal to 0, 1 to etc. m. What is the generating function for the sequence a0, a1, a2, etc. am? Solution. The generating function for the sequence is g of x equal to c of m comma 0 plus c of m comma 1 into x plus c of m comma 2 into x square plus etc. plus c of m comma m into x power m. The binomial theorem shows that g of x equal to 1 plus x power m. Generating function can be used to solve a widely variety of counting problems. In particular, they can be used to count the number of combinations of various types. Find the number of solutions of E1 plus E2 plus E3 equal to 17, where E1, E2 and E3 are non-negative integers with 2 less than or equal to E1 less than or equal to 5, 3 less than or equal to E2 less than or equal to 6, and 4 less than or equal to E3 less than or equal to 7. Solutions. The number of solutions with the indicated constraints is the coefficient of x power 17 is the expansion of x square plus x cube plus x power 4 plus x power 5 into x cube plus x power 4 plus x power 5 plus x power 6 into x power 4 plus x power 5 plus x power 6 plus x power 7. This follows because we obtain a term equal to x power 17 is the product by picking a term in the first sum xe1, a term in the second sum xe2, and a term in the third sum xe3, where the exponents e1, e2, e3 satisfy the equations e1 plus e2 plus e3 equal to 17 and the given constraints. It is not hard to see that the coefficient of x power 17 in the product is 3. Hence, there are 3 solutions. Note that the calculating of this coefficient involves about as much work as enumerating all the solutions of the equation with the given constraints. However, the method that this illustrates often can be used to solve wide classes of counting problems with special formulae, as we will see. Furthermore, a computer algebra can be used to do such computations. In how many different ways can 8 identical cookies be distributed among 3 distinct children if each child receives at least 2 cookies and no more than 4 cookies? Solution. Because each child receives at least 2 but no more than 4 cookies for each child, there is a factor equal to x square plus x cube plus x power 4 is the generating function for the sequence Cn, where Cn is the number of ways to distribute n cookies. Because there are 3 children, this generating function is x square plus x cube plus x power 4 into 3. We need the coefficient of x power 8 in this product. The reason is that The exponent terms in the expansion correspond to the ways that 3 terms can be selected with one from each factor that have exponents adding up to 8. Furthermore, the exponents of the term from the first, second and third factors are the number of cookies the first, second and third children receive respectively. Computation shows that this coefficient equals 6. Hence, there are 6 ways to distribute the cookies so that each child receives at least 2 but no more than 4 cookies. The principle of inclusion-exclusion. Let A1, A2, etc. An be finite sets. Then A1 union A2 union etc. union An equal to summation 1 less than or equal to I less than or equal to n modulus of Ai minus summation 1 less than or equal to I less than j less than or equal to n modulus of Ai intersection Aj plus summation 1 less than or equal to I less than j less than k less than or equal to n modulus of Ai intersection Aj intersection Ak minus etc. plus minus 1 whole power n plus 1 modulus of A1 intersection A2 intersection etc. intersection Ak. The principle of inclusion-exclusion. Proof. We will prove the formula by showing that an element in the union is counted exactly once by the right hand side of the equation. Suppose that A is a member of exactly all of the sets A1, A2, etc. An, where 1 less than or equal to or less than or equal to n. This element is counted C of r, 1 times by modulus of Ai. It is counted C of r, 2 times by Ai intersection Aj. In general, it is counted C of r, m times by the summation involving m of the sets Ai. Thus, this element is counted exactly C of r, 1 minus C of r, 2 plus C of r, 3 minus etc. plus minus or plus 1 C of r, r times by the expression on the right hand side of this equation. We have C of r, 0 minus C of r, 1 plus C of r, 2 minus plus minus 1 or C of r, r equal to 0. Hence, 1 equal to C of r, 0 equal to C of r, 1 minus C of r, 2 plus etc. plus minus 1 or plus 1 C of r, r. Therefore, each element in the union is counted exactly once by the expression on the right hand side of the equation. This proves the principle of inclusion-exclusion. The inclusion-exclusion principle gives a formula for the number of elements in the union of n sets for every positive integer n. There are terms in this formula for the number of elements in the intersection of every non-empty subset of the collection of the n sets. Hence, there are 2n minus 1 terms in this formula. Give a formula for the number of elements in the union of 4 sets. Solution. Inclusion-exclusion principle shows that modulus of A1 union A2 union A3 union A4 equal to modulus of A1 plus modulus of A2 plus modulus of A3 plus modulus of A4 minus modulus of A1 intersection A2 minus modulus of A1 intersection A3 minus modulus of A1 intersection A4 minus modulus of A2 intersection A3 minus modulus of A2 intersection A4 minus modulus of A3 intersection A4 plus modulus of A1 intersection A2 intersection A3 plus modulus of A1 intersection A2 intersection A4 plus modulus of A1 intersection A3 intersection A4 plus modulus of A2 intersection A3 intersection A4 minus modulus of A1 intersection A2 intersection A3 intersection A4. Note that this formula contains 15 different terms, one for each non-empty subset of A1, A2, A3, A4. A total of 1,232 students have taken a course in Spanish, 879 have taken a course in French, and 114 have taken a course in Russian. Further, 103 have taken courses in both Spanish and French, 23 have taken courses in both Spanish and Russian, and 14 have taken courses in both French and Russian. If 2,092 students have taken at least one of Spanish, French, and Russian, how many students have taken a course in all 3 languages? Solution. Let S be the set of students who have taken a course in Spanish, F the set of students who have taken a course in French, and or the set of students who have taken a course in Russian. Then modulus of S equal to 1,232, modulus of F equal to 879, modulus of R equal to 114. Then Modulus of S intersection F equal to 103, that is called 103. Modulus of S intersection R equal to 23. Modulus of F intersection R equal to 14. And modulus of S union F union R equal to 2092. When we insert these quantities into the equation, modulus of S union F union R equal to modulus of S plus modulus of F plus modulus of R minus modulus of S intersection F minus modulus of S intersection R minus modulus of F intersection R plus modulus of S intersection F intersection R. We obtain 2092 equal to 1232 plus 879 plus 114 minus 103 minus 23 minus 14 plus modulus of S intersection F intersection R. We now solve for modulus of S intersection F intersection R. We find that modulus of S intersection F intersection R equal to 7. Therefore, there are 7 students who have taken courses in Spanish, French and Russian. Suppose that there are 1807 freshmen at your school. Of these, 453 are taking a course in computer science, 567 are taking a course in mathematics, and 299 are taking a course in both computer science and mathematics. How many are not taking a course either in computer science or in mathematics? Solution: to find the number of freshmen who are not taking a course in either mathematics or computer science, subtract the number that are taking a course in either of these subjects from the total number of freshmen. Let A be the set of all freshmen taking a course in computer science, and let B be the set of all freshmen taking a course in mathematics. It follows that modulus of A equal to 453, modulus of B equal to 567, and modulus of A intersection B equal to 299. The number of freshmen taking a course in either computer science or mathematics is modulus of A union B equal to modulus of A plus modulus of B minus modulus of A intersection B equal to 453 plus 567 minus 299 equal to 721. Consequently, there are 1807 minus 721 equal to 1086 freshmen who are not taking a course in computer science or mathematics. Conclusion: in this chapter, the user have covered the following aspects of combinatorics and recurrence relations: basic theorems on permutation and combination, pigeonhole principle, principle of inclusion and exclusion, ordinary and exponential generating function, recurrence relation, solving recurrence relation by substitution, solving recurrence relation by conversion to linear recurrence relation.